Okay, so I'm going to be going over the 1.5 practice problems today. And so, yeah, let's start from the beginning. It says the atom that contains only one electron in the highest occupied energy sublevel. So what you would have to do in this problem is you would have to write out all the sublevels, the electron configuration for each of these. And I did that over here. So you see sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. And the question is asking which has only one electron in the highest sublevel. And so if you look here, right, so this has 4, this has 2, and this one has 1. So it's 4p1. And so the answer for question number 1 would be C, because it's the only answer choice with the 1 in the highest energy sublevel. And yeah, so this is a pretty straightforward question. Okay, let's look at question number 2. Which atom has exactly 2 unpaired electrons? So this one requires an extra step. This one requires you to not only write down the sublevel, but then go and draw the boxes for the electron pairings. And so you can see that here, where I drew all the electron configurations for sulfur, and so some of them I even used the abbreviation here. So I used the abbreviation here for argon, krypton, right? And then I wrote them out, and so it's just asking for the unpaired electrons, and so here there would be no, whoops. Well, okay, so sorry, my camera. Here we go. All right, there we go. So here, 1s2 is not something we would have to worry about. 2s2 is not something we'd have to worry about. The unpaired ones would be here, right? Because, right, so even in this one, they're both occupied, so there's nothing unpaired about this, right? But you have to remember, for p, there are 6 electrons, right? And so it's kind of like sitting in a bus. Like you would first go and sit here, and the next person would sit here, so there'd be an up here. And the next one, once all 3, because remember, electrons are all negative, so they repel, so they don't want to be next to each other unless they absolutely have to. But the question asks for which one has 2 unpaired, and so the only one here that has 2 unpaired are these 2. These are unpaired. So the answer to this question would be sulfur. Okay, let's look at the next question. Which of the following ground state electron configuration represents the atom that has the lowest ionization energy? Okay, so first of all, what is ionization energy, right? It's how easy it is to remove one electron. That's the ionization energy. So as you go down a group, you get less ionization energy because it gets more and more difficult. And then as you go across a period, it gets easier to remove an electron. So you increase your ionization energy as you go across a period. So the general trend is in the top right corner, it is most easy to remove an electron, and the bottom left corner has the least ionization energy. So if we look here, if we just look up lithium, carbon, neon, and sodium in a periodic table. Okay, so lithium is here, carbon is here, neon and sodium, neon and then sodium. The one that is, wait, is it, which one, what is it asking about? Has the lowest first ionization energy. So they're asking which one has the most difficult one to remove. We would look down here, and it would be sodium, because of all of them, this one has the least. It is the most difficult to remove an electron from. Oh, sorry. Here's sodium. So, moving on. Which of the following is the ground state electron configurations for F fluorine with a negative, right? So F minus ion. Okay, so this is just fluorine with an extra electron. So fluorine would be 1s2, right? Then 2s2, and then 2p1, 2, 3, 4, 5. It would be 2p5, and then if we add one more electron, where are we at? If we add one more electron, then it would just be 2p6. This has the negative, just indicates it has one extra electron. Okay, that wasn't difficult. Okay, number 5. Which of the following represents the ground state electron configuration for an atom of selenium? Oh, this should be easy. So let's see. First, we got to find selenium. Okay, selenium's all the way over here. I think there's a point to this question. Okay, so you can see the whole periodic table. And so selenium, you would have to first start out with, obviously, 1s2, right? That's the first row. And then 2s2. And then 2p6, all 6 of these, 2p6. And then 3s2, right? And then 3p6. Now here's kind of the wrench. You don't go to 4s. This technically is the next subshell. So you go 3p6 and then 3d10. And so we're still not at 34, which is where selenium is. So we put 3d10, and then we go to 4s2. Oh, I'm sorry. Then we go to 4s2 here, and then we go to 4p1, 2, 3, 4. So that's 1s2, 2s2, 2p6, 3s2, 3p6, and then you drop down and you consider this, because this is 3d. The first row is 3d, and this is 4d, and this is 5d, and then so on and so forth. And so you do 3d10, then you do 4s2, and then you do 4p4. So that's the answer for selenium. Okay, next problem. Trying to keep the, not try to, yap so much. Okay, so this one is fairly easy. How many protons, neutrons, and electrons are in so then this number up here, we should know that that's the mass, right? Let me zoom in a bit if I can. Oh, okay. So that number up there is the mass. So you don't even need to see the answer choice. Anything, a question like this, an answer choice will confuse you. And this is the number of protons. So you guys should know. So already 26 protons, right? And then to figure out neutrons, you just subtract the mass and the number of protons. And 56 minus 26 is 30. And then the electrons are just the same because they didn't give you a charge here, did they? No, they didn't give you a charge here. If I can get this to work. They did not give you a charge here. And so you are just assuming that they is a neutral atom. And if it's a neutral atom, the protons equal the electrons. Long story short, 26 protons, 26 electrons. And then we subtracted to find the neutrons. Okay, moving on. Good gosh. Okay, I'm not going to zoom in anymore because I don't think that worked well for me. So number 7, it asks, of the following electron configurations of neutral atoms, which represents an atom in an excited state. And remember that lab that we did where we saw all those colors? Those were electrons in the fire, with the chemicals in the fire. And those were electrons jumping from an excited state and coming back down. So excited state just means the energy, the electron is in a higher energy level than it would normally be. But it still has the same number of electrons. So all you're really looking for in this problem is one of them that is not in its normal state and that it is in a higher state than it should be. That it hasn't completely filled all of them and it's in a higher state. And so if we look here, it's 1s2, 2s2, 2p5. These are filled. 1s2 is filled, 2s2 is filled. It couldn't be this. This is not an excited state. Now, if we look at B, it's 1s2, 2s2, 2p5. Why isn't this a 6? So this is the one that's in an excited state because the electron that should be in the 2p6 has jumped up to 3s. And so even the rest of these, 1s2, 2s2, 2p6, that's normal. 1s2, 2s2, 2p6, 3s is normal. 3s2 is normal. 1s2, 2s2, 2p6, 3s2. These are all normal besides B. And so B is the one that has an electron in an excited state. Okay, question number 8. A lot of people had concerns and questions about question number 8. So question number 8 says, the effective nuclear charge experienced by the outermost electron of sodium is different than the effective nuclear charge experienced by the outermost electron of neon. This difference best accounts for which of the following? Okay, so first off, what is effective nuclear charge? So effective nuclear charge is the net positive charge felt by an electron after it is shielded from its inner electrons. So, like how much of the positive charge do they feel, right? So a high effective nuclear charge means that the electrons are held tightly, and that means they have a higher ionization energy. And a lower effective nuclear charge means that they are easier to remove. That means they have a lower ionization energy. Now, if we look at, so we're comparing sodium and neon, because that's the problem. Talks about sodium and neon. And if you look here, I wrote out sodium's electron configuration. So it is 1s2, 2s2, 2p6, and its outer electrons are in the 2p subshell, right? And so it has a very high effective nuclear charge. It's going to hold on to all of its electrons. They're kind of in their place, and everybody's happy. But here, we have an outer electron in the 3s shell. So that means it's further away, and it's shielded by the full 2p6. It has a whole extra layer of shielding, right? So this one has the lower effective nuclear charge as an outermost shell. So, these are easier to remove, it's because it is an underlying outer electron. And so it doesn't feel the protons pull as much naturally, right? Because it is so far away. So it has a lower effective nuclear charge, which means it is easier to remove. And so that's the answer. Okay. So it's a lower ionization energies would be the answer. I think that's B. Okay, and let's see the next question. Which of the following is the electron configuration of an excited atom that is likely to emit a quantum of energy? So, which one is likely to emit a quantum of energy? So it's just saying all right, so a quantum of energy is, at least I understand it, is the energy it releases as light. So this is similar to the lab that we did. Electron emitting photon. Okay, and so what I'm about to show you is how we kind of get to see light. And I had this up on the board when we did that lab, and this just shows that electrons, they jump up and they get some energy absorbed into them, and so look, they jump up, and then when they come back down here, they release a photon. And so that's kind of the light that we see, and especially in neon lights and such. Okay, and so this is similar to question number 7, because we are looking for which one is excited and which one is in a higher energy orbital, and which could fall back down. So we're just looking, and we're looking to see. So 1s2 is full, 2s2, 2p6 is full, 3s2 is full. So there's no reason to even look at the last one. We're looking for something in an excited state, somewhere where the electron has jumped up. And so this one is 1s2, 2s2, 2p3, 3s2, 3p, 3p5. Okay, and so there's nothing here. How about this? 1s2, 2s2, 2p6. How about this one? 1s2, 2s2, 2p6. So that only leaves us E. 1s2, 2s2, 2p6, 3s1. So this 1 is what's stopping us from having a full subshell. So the one that is excited is E, because it should be 3s2. Okay. Moving on to number 10. Oh, this one is also super easy. Okay, so which of the following represents a pair of isotopes? And you should have in your notebook, an isotope is something that has the same number of protons, but a different number of neutrons. So you quickly can just check. Not the same number of protons, because the atomic number equals the protons. Not the same number of protons. Not the same number of protons. The same number of protons, and not the same number. So it's only D, without even checking anything else. It's only D. They didn't even make this hard. They should have put one with another 7 and a 7 here, and the same mass numbers. As these two, obviously, would have different number of neutrons, but they have the same number of protons, right? And so the only answer could be D, and this was a relatively easy question. Okay, question number 11. Which of the following represents the ground state electron configuration of, I believe, manganese 3+ ion? So normally manganese is 4s2 3d5, because let's see here, manganese Mn. Right here. So, right, 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d4 is 3d 1, 3d2, 3d3, 3d4. Okay. So, but that's not what they're asking us for. They're asking us for Mn3 plus, if we look here. So that means something with 3 plus has lost 3 electrons, which makes it, pretty light on the electron. So it's definitely not the same as regular neutral Mn, right? And so neutral Mn, as I've written it in the abbreviated form, is 4s2 3d5, right? But I just wanted to remind you that you would lose these two first because they're the higher level. You lose the electrons from the higher level. So we're trying to lose 3 because, this is Mn as it is normally. So you would lose the 4s2 entirely, and you would lose 1 from 3d5, making it 1s2, 2s2, 2p6, 3s2, 3p6, and then instead of we lose the 4s2 and then we lose 1 from 3d. So it goes from 4s2, 3d5 to just 3d4. So we lose 2 from 4s2 and 1 from 3d5, turning it into this. Okay. Next problem. Okay, which of the following shows the correct number of protons, neutrons, and electrons in a neutral cesium-134? Oh, that's pretty easy. Cesium, you would just look it up. Jesus Christ. Who's calling me at this hour? Okay, so cesium is here. That has a atomic number of 55. And so off the bat, 55, right? Protons. And they didn't give us a charge, so the electrons have to be 55 too. And off the bat, we can remove C, D, and E, and then remove subtract 55 from 134, and that gets you 79. So the answer is B. That was a pretty easy one too. Okay. And so now the quick checks. So the quick checks, 1A is asking us what the atomic radius of Li, lithium, is larger than Be, and well, that's true because Li and Be are very similar. If you look at the periodic table, they're right next to each other, right? But Li and Be, right? Be has one more proton, which makes it Be, and it naturally comes with one more electron. And so that makes their attractive forces stronger, making the radius smaller. So you should write that down in your notebook. Okay, so the next question is 1B. The second ionization. Now, what does that mean, the second ionization? Second ionization is how much energy is required to move a second electron. Because remember, ionization energy is like the energy it takes to remove one electron. Second ionization energy is the energy it takes to remove a second electron after one has already been removed. Right? And so if you look, let me see the question. The second ionization of potassium is greater than the second ionization of calcium. And that makes sense because, what does it say again? The second ionization of potassium is greater than the second ionization of calcium. Well, yeah, once you remove this first electron, then the next electron shell would have 8, and so once you remove the first one from potassium, it has 8 full. It has a full octet, and so it loses one from there. Next question. The carbon-to-carbon bond energy in C2H4 is greater than C2H6, and so kind of drew C2H4 and C2H6, and so C2H4 has a double bond, right? And C2H6 has a single bond. And so when you have a single bond, you just have something called a sigma bond. And so if you look here, these are sigma bonds and pi bonds, right? So right here is a pi bond, and right here is a sigma bond. But when you have a double bond, you have both. You see? So here, this just has a sigma bond, and this one has a sigma bond and a pi bond, making its bond a lot greater. Okay, moving on. Okay, the boiling point of Cl2 is lower than the boiling point of Br2. So that only just has to do with, since they're very similar, right? That just has to do with their London dispersion forces, which we learned last year, but I guess we'll have to re-jog our memories with that. So, whichever one has the higher boiling point has the higher London dispersion forces. And so, like, how do you figure out which one has the higher London dispersion forces? The one with the bigger mass, if you remember from last year. And because bromium has a bigger mass, then it has a higher London dispersion force, and so thus it has a higher boiling point. Okay, moving on. Okay, consider the two chemical species, sulfur and sulfur 2 minus. Write the electron configuration of each. That's pretty easy. So S2 minus just has 2 extra electrons, which I've written out. So this is S as it is normally, sulfur. 1s2, 2s2, 2p6, 3s2, 3p4. You can refer to the periodic table. And this one just has 2 extra electrons. That's how it gets the -2 charge. Okay, the next question. Explain why the radius of S2 minus ion is larger than the radius of, well, that makes sense. Well, this one, S2 minus, has 2 extra electrons. And those 2 extra electrons, you think they get along with everybody in that outer shell? No. They're in 3p6, right? They done made it 3p6, but there's no protons to be coupled with them. So when you add protons and electrons together as you go across a period, the attraction becomes stronger because there are higher magnetic forces. But in this example, you're just adding electrons, no protons extra. So because there are more electrons in the p subshells, the outer ring creates a greater repulsion, and this makes the radius larger, right? Okay, and then which 2 species would be attracted in a magnetic field? Oh, okay, so if you look at so S, or sulfur, has a 3p4, and 3p6 is for S2 minus, and so this one has 2 unpaired electrons. And so the 2 unpaired electrons would make it so that it is paramagnetic, which means it has 1 or more unpaired electrons. And this causes attraction. The unpaired electrons causes things to be attracted to it, because it's like increases the magnetism, and it causes things to be attracted to it. Okay, now The S2 minus ion is isoelectric with the Ar atom. From which species, S2 or Ar, is it easier to remove an electron? So it's basically asking about ionization energy, right? So if you look, right, S2 minus has naturally it's sulfur, so it has 16 protons and it has 18 electrons. But argon has 18 protons and 18 electrons, and because it has more protons, the electrons are held tighter. It has more charge to pull it together, and this is called positive nuclear charge. And so since this one has sufficient protons to keep the electrons tighter, it's easier to take a electron from sulfur. And that's all for today. Make sure all these notes are inside of your here. I'll do a quick scan. You should have all these as notes in your notebook. So that's question 1. You can pause the video at any point, and you should, have explanations in your notebook for each of the questions. Three, and you can pause at any point to copy this down into your notebook. Question number 10, 11, 12. And this is 1A, B, and C. Okay, and then this is 1D. 2A. And then, I give you guys open notebooks, so you should take advantage because I may ask you questions. I will definitely ask you questions from here. All right.